Welcome to today's Explainer. Have you ever actually stopped to wonder how a physical spark of electricity becomes the data you see on a dashboard halfway across the world? It is a genuinely fascinating transition. Today, we're going to reverse engineer the anatomy of a smart device together. We're starting at the absolute ground floor with raw electrons, and we're going to build our way all the way up to global IoT connectivity.
Okay, let's dive right into this. Here's the roadmap for our journey. We'll start with the pillars of electricity, move into physical components and circuits, explore the microcontroller brain, and finally, cast our net into the IoT connectivity web.
Starting off with Section 1, the pillars of electricity, the holy trinity of electronics.
We're all familiar with Ohm's law, right? V equals I times R. Just as a quick refresher, think of it like a plumbing system. Voltage is the water pressure pushing the energy through, current is the actual flow of that water, and resistance is the size of the pipe opposing it. So voltage drives, current flows, and resistance opposes.
Now, when we arrange these electrical paths, a series circuit keeps the current in a single continuous loop. It's kind of like those cheap string lights. If one single bulb fails, it takes down the entire system. On the flip side, a parallel circuit, which is what you have in your home's wiring, splits that current up. This brilliantly prevents a single point of failure, meaning if one thing breaks, the rest of the circuit keeps humming along just fine.
Moving right along to Section 2, components and circuits, the actual building blocks of hardware.
All right, let's look at capacitors. I want you to think of capacitors literally like water balloons for energy. When you hit them with a voltage, they fill up with charge almost instantaneously, and they can release it just as quickly. They are absolutely fantastic for smoothing out noisy power supplies or setting up precise timing delays. It's a beautifully simple concept, really. They just store and dump energy exactly when the circuit demands it, keeping everything stable. Let's see how this builds into more active components.
Enter the operational amplifier, or op-amp. As Horowitz and Hill point out in their famous quote from The Art of Electronics, op-amps have a bit of magic to them. They're basically the Swiss Army knife of electronics. Say you have a tiny, incredibly weak signal, maybe from a temperature sensor or a heart rate monitor. An op-amp acts like a magnifying glass. It takes that microscopic voltage and powerfully amplifies it so the rest of your system can actually do something with it.
And then, of course, we have transistors, the ultimate electronic switches. Take the classic BJT, which uses a tiny current to control a much larger current. That's perfect for small loads like LEDs. But then compare that to the MOSFET, which is driven purely by voltage and is incredibly fast. This brilliantly illustrates a core concept in engineering, how we can use a delicate, tiny signal from a microchip to safely switch on a massive, power-hungry motor without blowing the whole thing up.
So, right now we've got a solid analog circuit. It can measure temperature, amplify signals, and switch on motors. But here is the million-dollar question. How does it actually think about that data? How does it make decisions?
That brings us perfectly to Section 3, the microcontroller brain, bringing logic to electronics.
When you want to add a brain to a device, you basically have a choice. You could use a microprocessor, like the one sitting in your laptop. It's incredibly powerful, sure, but it's demanding. It needs external RAM, heavy operating systems, and a ton of power. On the other hand, you have the microcontroller. It's got the CPU, the memory, and the hardware inputs all baked into one single, cheap, low-power chip. So the crucial point here is this. For embedded systems, like a smart thermostat or a drone, the microcontroller is the undisputed king. You get direct, real-time control over physical hardware in a tiny little footprint.
But what is that little brain actually doing? Well, it's performing a heartbeat known as the fetch, decode, execute cycle. First, it fetches an instruction from memory. Next, it decodes that instruction to figure out what it actually means, like is it adding numbers, is it turning on a pin? Finally, it executes the command using its arithmetic logic unit. What's truly wild is that a standard microcontroller loops this exact three-step process millions, sometimes hundreds of millions of times every single second.
Now, as incredible as these chips are, they are also incredibly sensitive. If you're building a smart device, this engineering checklist is practically non-negotiable. Throwing in decoupling capacitors at every power pin catches noise before it glitches your chip. Using a solid ground plane gives your signals a nice clean return path. Tying down floating pins stops them from randomly triggering based on literal static in the air. And those flyback diodes? They stop high voltage spikes from your motors from instantly frying your microcontroller. It's all about preventing erratic behavior before it even starts.
All right, so we've successfully built a localized digital brain. It's reading analog sensors, making digital decisions, and controlling physical hardware safely. But let's be real, an isolated smart device isn't really that smart. How does it talk to the rest of the world?
That leads us to our final stop, Section 4, the IoT connectivity web, networking the physical world.
Choosing exactly how your device communicates is arguably your biggest architectural decision. Honestly, picking the right protocol based on range and power is going to save you weeks of development time. Need to send data across a 15-kilometer farm using just a single battery? You're going to want LoRaWAN. Building a wearable fitness tracker? BLE 5.0 is your best friend. Doing smart home automation with self-healing mesh networks? Go with Zigbee. But if you want to push sensor data directly to a cloud dashboard over Wi-Fi, MQTT is the absolute industry standard.
Speaking of MQTT, it uses this brilliant publish and subscribe pattern, and it allows you to dictate exactly how reliable your message needs to be using quality of service, or QoS levels. QoS 0 is basically fire and forget. It's super fast, but if the internet blips, that data's just gone, which is fine for a temperature sensor that's reading every single second. QoS 1 guarantees the message arrives at least once, making it perfect for an alarm trigger. And QoS 2? That uses a complex four-way handshake to guarantee the message arrives exactly once, with zero duplicates. You'd use that for critical stuff like financial billing or remote commands.
Now, you might be wondering, why not just use standard web protocols like HTTP? Well, there is a stark contrast in network efficiency here. HTTP is fantastic for web APIs, for sure, but it is super heavy. It uses these massive text headers that'll drain a tiny battery dry just trying to send a couple of numbers. CoAP, on the other hand, is essentially the IoT version of HTTP. It literally shrinks the network overhead down to a tiny 4-byte header. For a constrained battery-operated microcontroller, that level of efficiency is the difference between your battery lasting a week versus lasting an entire year.
But listen, with global connectivity comes global risk. Security isn't just an afterthought here, it is absolutely paramount. To prevent your newly built devices from becoming part of some malicious botnet, you have to follow these golden rules. Never ever hard-code Wi-Fi passwords in plain text in your code. Always encrypt your data in transit using TLS to prevent man-in-the-middle sniffing. And critically, if your device accepts remote commands, you absolutely must strictly whitelist them. If you don't, a hacker can easily inject malicious payloads and just take total control of your hardware.
Okay, let's pull the whole shebang together into a real-world architecture, a complete IoT weather station. Step 1 is our physical hardware layer. We have an ESP32 microcontroller using its digital logic to read a physical temperature sensor. Step 2, the network layer. That ESP32 packages the data and securely publishes it over Wi-Fi via MQTT to a central broker. Step 3, a processing engine. Something like Node-RED catches that data and routes it. And finally, Step 4, the data lands in a cloud database and instantly updates a beautiful, real-time Grafana dashboard right on your laptop. Literally from a tiny electron moving through a sensor to global actionable data. And there you have it. You've just traced the entire journey. You understand the complete anatomy of a smart device, from the physical pillars of electricity, up through the logic of microcontrollers, all the way to the IoT protocols that network our planet. The foundational layers of modern technology are entirely in your grasp right now. So, the only question left to ask is, what will you build next? Thank you so much for joining me on this explainer. Stay curious and happy building.